Colin,
Cool.
you want a quick intro? Yeah.
Yeah, so our next speaker is Frank Hutter. Frank is a professor of computer science at the University of Freiburg, and he's also the chief AutoML expert at the Bosch Center for AI. Frank has co-organized the ICML workshop on AutoML for the last 6 years, and he's also given a NeurIPS 2018 tutorial on AutoML. Today, he'll be talking about AutoML. So Frank, feel free to take it away.
Right, could you allow screen sharing?
Yeah.
Thank you. So I actually pre-taped my talk an hour ago, just in order to actually be able to directly answer questions in the chat during the talk, and not only do the Q&A in the end, but have this more interactive. Can you hear this? Hi, I'm very excited.
Yep, we can hear it just fine.
Okay, then, well, this is me talking an hour ago, and I'll be answering directly in the chat. Hi, I'm very excited to talk to you about AutoML, AI that builds AI. In this talk, I will cover quite a range of AutoML methods. And to allow you to review the material afterwards, I made my slides available under this link here, automl.org/talks. In my slides, I also have a lot of references, and all these references are hyperlinks. So you can directly download the PDF, follow along, and dive into the material that interests you most. Now, to motivate AutoML, let's actually start by looking at the success story of deep learning. So given some data, the traditional machine learning had as one part of its workflow this manual feature engineering step. And this would actually be interdependent with the actual machine learning. And what made deep learning so successful is that it allowed to bypass this manual step and integrate it directly into this end-to-end deep learning pipeline that would learn useful representations of the input data and then useful models given those representations. However, as it turns out, even deep learning is not as end-to-end as we would like. Rather, the manual feature engineering step from before here is now just replaced by a manual step where a deep learning expert chooses the architecture and the hyperparameters in order to actually power this deep learning that is end-to-end. And even experts in deep learning need several manual iterations to identify the right architecture and the right hyperparameters to get strong performance on a new data set. And in contrast, AutoML really aims at true end-to-end learning. In goes the data, and then you start learning without the need for a domain expert or a human deep learning expert in the loop. Now, one way to achieve this is, of course, to mimic what the deep learning expert does and have a meta-level learning and optimization process that learns about the performance of this learning box here with different input architectures, with different input hyperparameters, learns across data sets for which data set, which type of architecture and hyperparameter setting performs well. You could even learn better optimizers for deep learning, etc. All of that is part of AutoML. And the nice things about AutoML is that it promises to yield results faster. So if you have a deep learning expert, they would be very happy to not have to do the manual architecture and hyperparameter optimization, but to actually just use automated tools and therefore become more efficient. And once they're more efficient, then it's of course also cheaper because, well, machine learning experts tend to be relatively expensive. And if they get their work done faster, then that's good. And as I will show, and as many papers have shown, actually the final performance can actually also be better than that manually found. And as a final bonus, with this process, you get a fully reproducible pipeline, and you don't depend as much on the manual design steps that your particular deep learning expert took. And so as a science, then machine learning actually becomes a bit more reproducible and therefore also transparent. Now, one note is that in enterprise AI, often this data here that goes into the process is actually not the typical data that we use in deep learning. It's not our typical images or speech or text, but rather what we actually often have in enterprise AI is tabular data. So for example, in human resources, we would know about the pay grade of an employee and their age and their performance and all kinds of features that we have in tables. And that is our input data. So and for that type of input data, actually, traditionally, deep learning hasn't been state of the art, but more traditional machine learning methods such as gradient boosting have actually dominated the state of the art. And we will actually get back to that later in the talk. Now, before we go into some current work on AutoML, I would like to acknowledge the decades of related work on AutoML that we have available to build on. So back in the 1990s, there have been a lot of different works on neuroevolution, which are actually quite similar to some of the current neural architecture search methods. Then in 2002, there was this RapidMiner software, which already did a grid search for entire chains of operators, so searching over a part of the machine learning pipeline and approximating automated machine learning to some degree. Of course, grid search is not a very efficient method when you go to high dimensions, but still, the main idea was already there. And then in 2009, there was this particle swarm model selection paper that did so-called full model selection, again approximating the methods that we use in AutoML to search over a large different set of methods. And then in 2011, 2012, there were a lot of Bayesian optimization methods that became popular. And in 2013, we used the method SMAC that we proposed in 2011 to propose what I would call the first real AutoML system, AutoWeka, which was wrapped around the Weka machine learning framework and really tried to give you machine learning at the touch of a button. And you wouldn't need to know about the 22 different machine learning algorithms in Weka or their up to 10 hyperparameters. You would just say, here's my data, go. And well, that of course was not the end. And in the same year, actually, James Bergstra introduced this paper, Making a Science of Model Search, in which he optimized hundreds of dimensions of vision architectures, including convolutional architectures, getting state-of-the-art on some data sets. So this was already very early, very strong work on joint neural architecture search and hyperparameter optimization. Then in 2014, we actually started the yearly AutoML workshop that, if you don't know it, I strongly recommend. We are still running it at ICML every year. And then in 2015, there were these two AutoML frameworks, particular AutoScaLearn, that is actually still quite popular. In 2016, we had the first automated deep learning tool that actually won a competition against humans, so a data set in a competition. And then in 2017, neural architecture search hit mainstream with this paper, Neural Architecture Search with Reinforcement Learning by Sof and Lee, that really made neural architecture search and AutoML very popular. And after that, we really saw an explosion of work on AutoML and neural architecture search. For example, in 2019, there was the STARTS approach that made the computational complexity much smaller, so made it much more efficient to search for neural architectures, and we'll actually talk about that in a little bit more detail. And it's not like nothing happened in this time here, but I needed the space for this plot here. Actually, a lot happened. The number of papers on neural architecture search is actually growing exponentially these days. There's over 250 papers, about 250 papers in 2019, and there were, I think, about 400 or so in 2020. So it's really growing very quickly. Now, having covered this brief history of AutoML, here are the topics I will discuss today. First, having seen this exponential growth of neural architecture search papers, And because neural architecture search is such a young field, it's really important to establish best practices and benchmarks in order to guide all of this research. So that's what we'll talk about first. Then we'll talk about speed-up techniques for neural architecture search, because, for example, the work by Sof and Lee used something like 800 GPUs for 2 weeks, which is, of course, not sustainable. And last, we'll talk about extensions of neural architecture search, in particular joint neural architecture search and hyperparameter optimization, and also searching for multiple neural architectures at the same time that can be combined nicely into an ensemble. Now let's dive right in with best practices and benchmarks. Over the last year, there have actually been several papers that showcased issues in neural architecture search. And I would like to address these head-on in a talk that will focus a lot on neural architecture search. So let's get this out of the way. There are some papers showing that actually neural architecture search methods can sometimes perform worse than random or not much better than random. The reproducibility is poor, and even actually random seeds can make quite a dramatic difference. Then the training pipeline actually matters much more than the architecture sometimes. And well, there's some poor scientific practices in this young community, such as not having code available or having incomparable training code, search spaces, evaluation schemes, which makes it very hard to make progress as a community. So here, a visualization of this issue that training pipeline can matter more than the architecture. This is from this paper, NAS evaluation is frustratingly hard, that showed basically the performance on a search space from the starts algorithm. Here, the baseline performance, something like 95% accuracy on CIFAR10. And as they added more and more tweaks to the training pipeline, such as data augmentation and different types of regularization and so on, and also made the architecture larger and tweaked the hyperparameters, you can actually get to something like almost 98%. In contrast, the range of performance you get from just changing the architecture is more in the order of 0.5%. So 0.5% compared to this jump of 3%. So that goes to show that really the hyperparameters and the training pipeline are very important. And well, we often see tables like this in neural architecture search papers. And this is just not the type of table that is helpful, because all these different methods are really incomparable if they use different training pipelines, different search spaces, and different evaluation schemes. And therefore, we need to establish these best practices. Fortunately, the community has recently actually been working on addressing these issues quite a lot. And one of the most important tools for these are these tabular neural architecture search benchmarks, which enable fair and efficient evaluations of our NAS methods, multiple runs, ablation studies, and all the things that you want to do in an established scientific framework. We've also established this best practice checklist for scientific research in NAS, and we've started the neural architecture search workshops at iClear that are now annual. And finally, we also have this NASLib library that enables empirical comparisons without confounding factors. Now, I want to talk a bit more about these tabular benchmarks, and I also want to talk about a new type of benchmark that actually goes beyond tabular benchmarks, so-called surrogate neural architecture search benchmark. But first, let's have a look at the first neural architecture search benchmark, NASBench 101. Now, this is a benchmark that I introduced together with very brilliant collaborators at Google. Here we evaluated 423,000 different architectures in a small cell search space, and therefore thereby covered this search space exhaustively. And now we can actually, well, run neural architecture search experiments in the search space in minutes on a laptop. Of course, this is only possible because we have saved the results of these 423,000 architectures, running which actually took 4,000 TPUs for several months. So this was really only possible with Google infrastructure, and I'm very thankful to Google for this collaboration. And this one-time cost already has far more than amortized. A lot of people have used this architecture benchmark. And now, as I said, we can actually evaluate NAS methods in minutes on a laptop. That really enables proper scientific research, multiple runs, robustness studies, fair head-to-head evaluations by design, because, well, the final evaluation pipeline that mattered so much, as we saw in this NAS evaluation is frustratingly hard, that is fixed for all these 423,000 architectures. And of course, source code and scripts are available. So one of the things that you can do with NASBench 101 is compare different optimizers. And here's a plot from the paper that shows that actually, well, random search is the worst approach, reinforcement learning is a bit better, and then here, regularized evolution and Bayesian optimization are actually amongst the best methods. And this already goes to show well, that this method SMAC, which is a Bayesian optimization method based on random forest that is from 2011, actually outperformed the reinforcement learning approach from 2017. However, of course, in 2017, well, they couldn't have known because, well, with 800 GPUs in 2 weeks, they could afford exactly a single run of the RL method. And there's a lot of noise, and it would have been really hard to run other methods. But now, with these tabular neural architecture search methods, we can actually do these analyses, and we can easily run each of these optimizers 500 times in minutes on a laptop. So that is what we gain from tabular benchmarks. And actually, modern and customized Bayesian optimization methods for neural architecture search have been shown to actually perform much better. For example, this Bananas paper or NASBOL, which are quite exciting. Now, I just talked about NASBench 101, which was the first neural architecture search benchmark. But one of the problems of all these tabular neural architecture search benchmarks is that, well, they're limited to small neural architecture search spaces that we can actually exhaustively evaluate. In practice, what we would rather want to evaluate are architecture search spaces that have something like 10 to the 18 architectures, such as in the DARTS paper. And this NASBench 301 now is the first cheap to evaluate neural architecture search benchmark that allows for arbitrarily large search spaces. And this is made possible by actually using a surrogate model rather than a tabular benchmark. Now, this goes as follows. So we observe results for some architectures, in our case actually 50,000, and then we fit a regression model to use instead of a table. So instead of querying a table, we query the regression model. And lo and behold, this can actually yield better estimates than a table. And the reason for that is that tabular benchmarks typically only use one or very few runs for an architecture A to estimate its performance, and do not take into account that similar architectures actually yield similar results. So it makes an independence assumption that is actually quite wasteful. It throws away information. And then from the perspective of machine learning, it makes actually a lot of sense that a model can do a lot better that takes into account the performance of neighboring architectures. And here we see a plot that shows that after something like 20,000 architectures that we fit our model on, our model starts to have a smaller error than the table, and the table is based on just a single run of SGD, and of course there's noise in SGD, and that's this noise here. And with a regression model, you can actually get below that noise level. Now, some details on NASBench 301. As I said, we evaluated 50,000 different architectures that we got by actually using a lot of different architecture search methods in order to really search the space, cover it well. And we evaluated a broad range of different regression models. And the best regression models turned out to be gradient boosting on the one hand and graph convolutional neural networks. And the estimation errors were lower than the error due to noise in a single run of SGD. And there in particular, the graph neural network actually worked best. Now, as for tabular benchmarks, we can benchmark NAS methods on NAS Bench 301. And as for tabular benchmarks, we have that the actual wall clock time that it takes when you run these methods on the real search space are enormous, actually larger than 1 GPU a year per run. And for the surrogate benchmarks, well, the simulated wall clock time here can actually be simulated within minutes. And the trajectories are still quite similar to when you run on the original benchmark. It's just that for the surrogate benchmarks, the main difference is that we actually have smoother curves. And this is because we can actually do a lot of runs. Here we could only afford one run for each of these methods. And here we could trivially afford hundreds of runs. All right, so I showed this slide here before. And now I just wanted to point out that with these surrogate benchmarks, I really hope that we can scale the success of these tabular benchmarks. And NAS Bench 101 was not the last. It was the first in many tabular NAS benchmarks. I hope that NAS Bench 301 can be the first of many surrogate NAS benchmarks to come, and therefore allow us to look at a lot of very interesting search spaces that we haven't been able to look at properly so far. And with those developments and all the other developments in the community, I believe we now have a quite solid foundation for a scientific NAS community. Now, next, I want to talk about speedup techniques for NAS. And I already alluded to this original work by Sof and Lee, taking 800 GPUs for 2 weeks, and that's, of course, not sustainable. So let's look at a few methods for getting faster. So overall, there's 4 different types of methods, or families of methods, that I would like to mention. The first one is weight sharing. And here we have approaches such as ENAS and darts, and I will actually talk about darts quite a bit, starting with the next slides. So I'll skip to the next point. There is also weight inheritance and network morphisms methods, which exploit that when you locally change an architecture, that then you can actually use a network morphism step in order to transfer the weights from the previous architecture to the new architecture, and then just do some fine-tuning steps. And therefore, you can actually relatively cheaply do local steps in the architecture space and then do basically a local search. And that can, well, that saves the time of training the network from scratch every time, but in each step, you just fine-tune a bit. And that can lead to very nice speedups. Meta-learning is another way for speeding up neural architecture search. And there we learn across data sets. And there's different things you can learn across data sets. One thing is to initialize architectural weights of darts. And there's some works for that. Another thing you could learn is a prior for black box optimization methods. So for example, for Bayesian optimization, or also for reinforcement learning. In multi-fidelity optimization, what you do is exploit cheaper proxy models for black box optimizers, in particular for Bayesian optimization. And there's also lots of very nice work on that. But here I want to talk a little bit more about weight sharing and one-shot models. Now, darts is a very popular approach that was introduced in this paper in 2019. And what it does is it relaxes this discrete neural architecture search problem here, where you have some tensors and you need to decide about these operations to use between these tensors, such as, for example, a 3x3 convolution or max pooling and so on. It replaces these by actually these mixed operators, where it just carries out all the different operations and then just averages over them. And each of the operations gets a weight, that is this alpha. And then it solves a bi-level optimization problem in order to optimize these alphas in a gradient-based manner, where it basically alternates gradient-based updates of the architectures, on the architectural weights alpha, and the weights that would minimize the training loss for these alphas. And this iterative gradient descent is actually not guaranteed to converge, but actually in practice it works quite well. And then finally, after you have optimized these architectural parameters, you discretize in order to obtain a single architecture, typically by taking the operation with the highest weight on each edge. Now that's a darts algorithm, and this darts algorithm is really has changed the name of the game of neural architecture search quite a bit. There have been literally hundreds of follow-up works and thousands of citations of this approach. And unfortunately, it still has some problems. And what we showed in one paper at iClear 2020 is that actually one of the problems is that darts can really fail horribly, returning degenerate architectures that consist of only skip connections. So all of these choices are made to be skip connections. And this was consistent across 12 different NAS benchmarks we studied, 4 different search spaces, 3 different data sets. Now that, of course, begs the question, why does darts fail? And while I mentioned before that the optimization is not guaranteed to converge, but, well, here we see training loss over time, and this is actually perfectly fine. Optimization is not the problem. Validation, actually also validation error shrinks over time. Training loss and validation error shrink. But the curvature over time increases. So we're going to a subspace where we have a steep local minimum where we do a small step in the alphas that small step in the alphas already leads to a large performance difference. And this is particularly bad in combination with the discretization step that darts does in the end, which actually is a quite substantial step in this architectural space. And so this performance loss by discretization indeed correlates with this curvature here, and that leads to this test error here increasing after an initial progress. So first we get nice test errors, but if we let darts run, it actually runs into the skip connection issue. And well, how can we avoid this? Well, we can avoid this high curvature, and that actually fixes darts, fixes the failure modes of darts. And how can we avoid this high curvature? Well, it's by regularization, and option 1 would just be early stopping based on an estimate of the curvature. Option 2 that we evaluated was a regularization of the inner objective by L2 or scheduled drop pass. And this led to nice results that, well, got the same performance as darts on CIFAR-10, which was the dataset used in the darts paper, but on a bunch of other data sets and also on these 12 different search spaces that we evaluated, it got much, much better performance and didn't run into the skip connection issue. And there's actually a lot of different follow-up papers proposing various different types of regularization. All right, so I briefly spoke about darts and that it can be stabilized by additional regularization. I didn't go into details on these other methods here, weight inheritance, meta-learning, multi-fidelity optimization. And if you're interested in those, I would like to refer you to my longer talk, NAS Coming of Age, that is linked here. Then without further ado, I'd like to go to the last point in the talk, extensions of neural architecture search. So first, to joint neural architecture search and hyperparameter optimization, and then to neural ensemble search. Now, recall this relative importance of hyperparameters that we saw before. The hyperparameters and the training pipeline was much more important than the architectures. So it's really the case that hyperparameter optimization is the hidden champion of AutoML, and we shouldn't undervalue it. And we should actually, when we search for neural architectures, we should also jointly search for the right hyperparameters to use with them. And we did that already back in 2015, where our approach then called AutoNet actually already won several data sets against human experts. And here's an example from a human action recognition data set with something like 55,000 data points, where, well, this AutoNet actually found an area under the curve of 0.9, and the best team of human experts in 2 months actually only got 0.8. Now, of course, we have moved on since 2015, and in the meantime, Now we are doing multi-fidelity optimization in order to speed this up, and meta-learning to warm start across data sets in order to speed this up. And this has yielded this Auto-PyTorch framework, which we only started quite recently, but which is already a fairly major open source project. Now, briefly, what we do actually to search in the space of Tabula for tabular data sets, we have a search space that looks at architectural choices and hyperparameters, and the architectural choices for these tabular data sets are basically different alternatives of ResNets, where we look at how many blocks are there, how many groups are there, and well, also different types of optimizers and learning rates, etc. And well, I briefly mentioned meta-learning before. So here we use meta-learning across 100 datasets to actually find strong initializations to search in the space of a combined space of 24 different dimensions, 12 architectural and 12 hyperparameter dimensions. And this meta-learning actually led to 100-fold speedups over searching from scratch for each new dataset. By actually meta-learning, we are much faster. And this also led to very competitive performance compared to other AutoML frameworks for tabular data, such as AutoKeras, AutoScaLearn, and HyperOptScaLearn. And we're running further evaluations right now to actually evaluate on this OpenML AutoML benchmark and also evaluate against AutoGluon together with the AutoGluon team. Now, this multi-fidelity meta-learning approach is not restricted to tabular data. It also works on image data. And here's an evaluation on this NASBench 201 dataset. There's only 3 datasets in this NAS benchmark, CIFAR10, CIFAR100, and downsampled ImageNet. So there's only 2 meta-trained datasets at a time. And nevertheless, the warm starting actually helped a lot. It's this purple curve here compared to starting from scratch, and actually led to a performance that is competitive with gradient-based neural architecture search, and in particular 4 times faster to reach 90% on CIFAR10 than GDAS or any other gradient-based approach we tried, including also DARTs. Now, the last thing I would like to say for joint NAS and HPO is that, well, we also looked at expanding the hyperparameter optimization space to look at a lot of different regularizers. So 13 different regularization methods listed over here. And we had as hyperparameters the choice of which regularizers to actually use, and then their subsidiary hyperparameters. And we actually for this used a fixed architecture. And surprisingly, this led to a new state-of-the-art model for tabular data. We evaluated this on 31 tabular data sets and compared it to both XGBoost, gradient boosting, and against TabNet, which is another approach for making deep learning scale to tabular data. And so we, of course, double and triple checking these results. And it's too early to claim for sure that there is a new state-of-the-art method for tabular data. But if this was the case, if these results hold, then I think this is really a major step forward for the deep learning community, because it would basically open a 4th pillar for deep learning applications next to vision and speech and text, which have been conquered by deep learning. But tabular data really has been immune to that so far, despite many people trying. And well, these results show that if you only regularize properly, then you can be better than XGBoost. And we really tried hard to make XGBoost as good as possible. We tried 4 different hyperparameter spaces for it. We tried implementations in AutoScaLearn of gradient boosting and XGBoost. And so far, we couldn't poke a hole. One disclaimer here, of course, is that we only used very clean data sets. They were quite balanced. There were no bad outliers. And so far, the runtime of these regularization cocktails is quite high. It's our budget for the optimization is 4 days. We, of course, also use that for XGBoost, but still 4 days is maybe not what we would want to spend on a typical tabular data set. Nevertheless, I think this is quite exciting, and we definitely have a lot of methods in mind for improving this and making this faster. All right, the final part of the talk is short, and it's on neural ensemble search. And here, the main point is that assembling often improves the performance of neural networks. This is well known, so-called deep ensembles, where you just build an ensemble of many different restarts of a neural network with different initializations, actually have state-of-the-art predictive uncertainty estimation and robustness to distributional shift in 2019. And this is despite the fact that diversity among base learners' predictions is key for strong ensembles. We know that. And so in order to exploit this diversity, we actually use neural architecture search to search for base learner architectures that, when you combine them, actually optimize ensemble performance. And so by optimizing ensemble performance, we implicitly optimize the trade-off between diversity on the one hand and the individual performance of the base learners on the other hand. And here is the result in a nutshell. So there's 6 different metrics here. There's the ensemble negative log likelihood, the error, and the expected calibration error. And all of these 3 different performance metrics are actually better for these neural ensembles than for the deep ensembles. And down here we have 3 different diagnostics, and we see that the neural ensemble search yields models that disagree more, so that don't agree as much, so the diversity is higher, but the individual errors are higher than for the deep ensembles. The deep ensembles here in particular are actually for the best architecture in this particular search space. It's also for NASBench 201. So despite the fact that we don't have the best architecture, we still, by having greater diversity, we get lower errors. So lower oracle negative log likelihood and also lower actual negative log likelihood and error and expected calibration error. And so this goes to show that searching for an ensemble of neural architectures is a good idea. Here's a quick visualization showing that different architectures actually make different predictions. So on the left here, we have predictions of 5 different architectures. These clusters here, and it's a t-SNE plot of the predictions. And on the right, we have predictions of the different architectures found by neural ensemble search compared to the ones of a single architecture. And finally, this neural ensemble search also yields robust performance under Datashift. So we used this CIFAR-10 dataset that had some validation corruptions and test corruptions. And, well, long story short, the performance is much better under these corruptions than for deep ensembles. And we get that by, during the neural ensemble search, actually randomly choosing one of these validation corruptions for each evaluation. So to wrap up, as a takeaway, AutoML and especially neural architecture search are really coming of age. A scientific community is forming around NAS with benchmarks and best practices. There's many ways to speed up neural architecture search nowadays, and there's exciting extensions of neural architecture search. Joint NAS and HPO can really give you true AutoML in the form of Auto-PyTorch and these regularization cocktails, and neural ensemble search can additionally also give you robustness to Datashift. All our code is available, also the slides here, and we also have a free book on AutoML. With that, thank you very much, and thanks to my team. And I'm looking forward to questions. Thanks. All right, back to live. How should we go about questions?
Frank, did you want to just pick a few questions and answer them?
Yeah, so I've been checking off as many questions as I could in the chat, but there is still some left. Good, so, well, I'm just going in the order that I saw them. I've been asked to basically write AutoML several times with the business case. We don't know what the customer wants to predict. How can we respond to the business that sees AutoML as a solution to all problems? I agree that that is something that customers sometimes say, oh, I just want to use machine learning for something. Here's my data. And of course, if the machine learning problem is not defined yet, then it's very hard to use AutoML. But what you could do actually as a consultant, etc., is you could look at the data and actually see which columns of the data, for example, could be easily predicted given the others. And then it's sort of this interactive talking to the customer. What would be actually useful for you? We could predict this from this. Would this be useful? We could predict this. Is that useful? But in the end of the day, you know, the domain the people from the domain need to know what they want. Okay, moving on. Hi, I'm curious about AutoML for enterprise AI. Does your book address suggestions for enterprise data? The book does not mention enterprise data as such, but there's a lot of AutoML for tabular data in there. In fact, almost everything in there is about tabular data because it was written just as neural architecture search and got really hot. And there is one review chapter there, in particular the survey on neural architecture search that I also posted, that's also published at JMLR, but the rest is actually on tabular data. And I think much of that will apply to enterprise data. Good, so then how is the memory consumption of Auto-PyTorch? Is it like a medium or big neural machine translator? No, really not at all. So, I mean, what I talked about is Auto-PyTorch Tabula. So that's for tabular data. And that's just something like a 10-layer residual neural network. For most tabular data sets, you don't need hundreds of layers. And you could do Auto-PyTorch for neural machine translators, etc., for NLP, but we haven't. All right. Yeah, so Ralph says, thanks for mentioning RapidMiner in your AutoML history review. From his questions, I think Ralph is affiliated somehow with RapidMiner. And he clarifies that in 2002, RapidMiner did actually not only offer grid optimization, but also evolutionary optimization. I'm not sure if this was also for the hyperparameters, but the reference I got from Katarina Morik about it was that grid search was implemented, but maybe that should be rectified. Thank you. Ralph had another interesting question. How does NAS relate to the no free lunch theorem? Is NAS not yet another meta-learning algorithm, and hence the no free lunch theorem should apply? The question went away. Sorry. Here it is. How do you know that your NAS benchmarks are similar enough and relevant to the real-world problems you want to solve in industry? That is a good question. So in terms of the NAS benchmarks, many of them are now being prepared by industry. And because of that, I think the gradient of where NAS is going is also going towards all those benchmarks that are prepared by industry. There's hardware where neural architecture search now, which is of course really good for coming up with small networks, for sensors and so on. So I think that is clearly an application area of interest to industry. Then on the other hand, efficient nets, etc., are found by neural architecture search. So that's more the realm of computer vision. For transformers, there was the evolved transformer, which was a NAS paper by Quockley that sort of incrementally improved it. But there, I think there's still a lot of possibilities for, using the domain experts' knowledge together with NAS algorithms in order to design the right search spaces, the right also training pipelines in order to really gain state-of-the-art performance for the problems that you care about. Okay, then let's move on. In which industry does Bosch apply NAS? there is one published paper where I'm not actually a co-author, but my former PhD student is. And they actually look at resilience. So it's a multi-objective optimization problem and resilience against errors. That is definitely an area where they apply it. And I think I'll leave it at that. Knowing Bosch's areas of work, I think you can figure out some other areas where they use it, but I didn't actually talk to them about what I can say.
We're about just running a little late, so maybe one last question.
Okay. Is it possible and practical to use NAS for the neural net in deep reinforcement learning? Yes, it is, and we have indeed done that. We have a paper on Auto-RL, actually for learning to design RNA at ICLR 219, and we have a paper called Surrogate that is actually a joint neural architecture search and hyperparameter optimization for off-policy RL. That's going to be at the next ICLR. I can put the links to that in the chat. And I can also look at maybe some of the other questions and answer some more in the chat. But thank you very much. This was awesome questions, and been such a pleasure to talk right after Peter Norvig and and Alan. But yeah, I definitely grew up with AI, a modern approach, and that was an honor to talk right after them.
That's great.
And awesome questions. Thank you, guys.
It's an honor to have you on. And as most people here probably know, we're a NAS and an AutoML company as well. So we're very, very privileged to be, collaborating with someone like Frank. Thank you.